All right, so the remaining deposition techniques that we're going to talk about is they have a little bit of a chemical flavor to them. We talk about bonding at the end of this lecture, but we discussed thermal oxidation as let's say the most basic growth, film growth mechanism that we know. Talked about physical vapor deposition, and now we want to make things a little bit more complex and actually take advantage of the chemistry in addition to the physics. So in a CVD process, the chamber looks as is shown here. You have an inlet that connects to different types of gases on the left side. Then you have wafers inside the chamber. The chamber is often heated, so you have a coil for heating the chamber to elevated temperatures to basically facilitate the chemical reactions. And then once the reactions happen at the surface of the wafers that you have in there, you need to get rid of the chemical byproducts. So this is a typical CVD chamber, chemical vapor deposition chamber. And the steps that you need to happen in the right order, well, in addition to have the right gases at the input, is that you need to bring those gases to the surface of your substrate. Once the gases are there, you need the gas molecules to be absorbed to the surface of your substrate, right? You want the gas molecules to settle down on the surface of your substrate. No penetration into the substrate, it's just settling down on the surface. And then hopefully they react with each other. In many cases, if you do the things right, the substrate itself will act as a catalyst. So it encourages or facilitates the reaction between the gas subspecies at the surface. And then once the reaction happens and you have the desired material, you want it to be left on the surface and the reaction byproducts to be taken away from the surface of your substrate. This is usually through a constant flow of gases. So you basically let gases come into your chamber at certain rates, and you keep removing the byproducts from the chamber. In theory, you can now deposit anything you want on the surface of your substrate. As long as the chemistry is right, you should be able to deposit anything you want. Because the temperatures are not so high and the reactions are happening relatively quickly, films are amorphous. So you get an amorphous film of, let's say, silicon dioxide if you use the right gases in there. If you use silicon, the precursors for depositing silicon, you don't get crystalline silicon on the surface, you get amorphous silicon or polysilicon, unless you do this at really high temperatures. So there is a flavor of CVD that is done at high temperatures, and you raise the temperature inside the chamber so high that the chemical byproduct, the chemical products, let's say the film that you want, those molecules have enough time to go and find the right place in the crystal and settle at the right locations. But in general, your films are amorphous films. CVD processes are usually categorized in 3 different groups. APCVD, or atmospheric pressure CVD, was the basic one that was developed the first in the 60s. And this is basically what we said, everything is happening under atmospheric pressure. The temperatures for reactions are about 700 to 1,000 degrees Celsius. And the challenge here is that at such high pressures, when you have a flow of material into your chamber, you have gas dynamic issues, right? So you can have vertices and all sorts of phenomena going on. They later found out that if they drop the pressure to tens of millitorr or maybe hundreds of millitorr range, they will have a lot more control over the flow of the gas inside the chamber. They will avoid all of those basically moving to more of a laminar flow compared to a turbulent flow if you drop the pressure. And by avoiding turbulence in your gas flow, you get better uniformity in your film thickness. The deposition is more predictable, more uniform across the wafers. And the good news is that by dropping the pressure, you also can make the reactions happen at lower temperatures as well. So in an LPCVD, low pressure CVD process, the situation is very similar to APCVD. We only drop the pressure to about hundreds of millitors, and we get better uniformity out of the expense that we put into developing such a system. However, the temperature is still fairly high, at least a few hundred degrees Celsius, 600-700 degrees Celsius. Now, you can make these gases react with each other by providing the energy that the initial energy that they need through a plasma. So instead of heating up the chamber so that those gases react with each other, you can actually create a plasma, and by having a plasma of these gases, there is a higher chance of them reacting, and those things will happen at lower temperatures. So this is called plasma enhanced CVD, happens at 200 degrees Celsius or maybe even less, and it gives you a lot of control. Like other plasma systems, you can play with the pressure, you can play with the gas concentration, you can play with the gas ratios, and also temperature too, right? It gives you a lot of buttons to press to tune different parameters. However, in terms of film quality, between these three methods, usually LPCVD gives you the best quality for the film. It doesn't give you as much freedom in terms of tuning the film properties as PECVD does, but the quality of the film, let's say if you're looking for high quality without defect film or without hydrogen left over in the film, LPCVD is usually your go-to method. If you are depositing films like polysilicon, you can dope them at the same time that you're depositing them, right? So if you're depositing a layer of polysilicon, just add a little bit of boron gas carrier to your mix, and you dope your polysilicon layer as you're depositing it. Mechanical properties as well as optical properties of these films can be controlled through process parameters, as expected. And one thing you can do is that sometimes you have recipes for depositing film with, let's say, known tensile stresses in them or known compressive stresses in them. What you can do is that you can alternate between these films and get a final sandwich of these layers of these different films with a good control over how much stress in these films you have. We'll see that the stress in the thin films is a big problem in MEMS. You want stress-free films in majority of cases, but a lot of these deposition techniques that we're dealing with don't give you that. You get a film on the surface of your substrate that has some compressive or tensile stress in it because of the fabrication methods, and there's always a need for controlling that stress or managing that stress somehow. So among the materials that are more commonly deposited using CVD is nitride, silicon nitride, which is used similar to silicon dioxide for isolation and chemical protection and so on and so forth. Compared to oxide, silicon nitride is more chemically stable. It is harder to remove. It is harder to etch. So in some situations where silicon dioxide may not provide the chemical protection you need, you may choose to use nitride. It can be deposited from a combination of ammonia and silane, and if you do this right, silane and ammonia, none of them are nice gases, both of them are very dangerous, you will get a film of silicon nitride on the surface of your substrate. If you want a cleaner film, instead of silane, you can use dichlorosilane. So you have a bit of chlorine in your gas mixture. And what happens is that during your process, you also produce HCl. And the function of that HCl, it is a byproduct, so you want it to be removed from the surface. But at the same time that you're removing it from the surface, or it leaves your surface, it also takes away some of the contaminants that you may have on the surface. The challenge here is that your CVD chamber has to be resistant to HCl, which is basically saying that it is going to be a lot more expensive. Typical thicknesses for nitride are 50 nanometers to maybe about half a micron. It's a relatively slow process. And the stress in the nitride film can be controlled fairly accurately, based on the history that people have had with silicon nitride. You can actually have a good control over the stress in the nitride field. Polysilicon and silicon dioxide are also deposited using CVD. Silicon dioxide, we know you can grow it, but to grow it you need to have access to the surface of your silicon wafer. In some cases you may not, right? So you may have already deposited the layer of silicon nitride on the surface, and you don't have access to that silicon to consume and use for a new film of oxide, and therefore you need to deposit oxide if that's the material you need. Polysilicon is essentially, in terms of mechanical properties, very similar to silicon. In terms of electrical properties, it is again, from the MEMS point of view, similar to silicon. You do not make transistors from polysilicon in most cases because of the problems you will have with leakage currents. But because of all those nice things that we said to silicon apply, 99% of them apply to polysilicon, at least from the mechanical point of view. It is very commonly used in MEMS as a structural material. And we deposit it using a CVD process. Again, it's silane that we bring to the surface of silicon, and if you do it right, you dissociate the molecule, have silicon on the surface, and get rid of hydrogen. If you do it right, and if you do it at elevated temperatures, you can grow crystalline silicon, a layer of silicon that follows the pattern, this crystalline structure of the substrate. Of course, you need to have exposure to the substrate. Your gas needs to see the substrate. You cannot do this on top of another layer. But if you do it right, you can epitaxially grow a layer of crystalline silicon. Silicon dioxide, as just mentioned, can also be deposited using CVD, and it's again silane plus oxygen, or dichlorosilane plus some form of oxygen carrier gas to give you the decolored SiO2 layer. Now, one problem that happens from time to time if you do not set the process parameters correctly is that you get some snowing effect. What that means is that your gases react above your substrate instead of on your substrate, right? So this is something that I maybe forgot to mention when I was talking why I want the gas molecules to be adsorbed to the surface first. That's because I want to avoid snowing, right? So I don't want the reaction to happen above the substrate and the byproduct fall onto the substrate. In that case, I will have very poor adhesion or no adhesion. So that's CVD, and that basically wraps up all of the major film deposition techniques that we have from microelectronics side, or inherited from microelectronics side. I'm going to cover a couple more that are, let's say, more MEMS specific in terms of their utilization. The first one is electroplating. It's a well-known technique. I think a lot of you are familiar with this from your high school chemistry. And this is where we put a seed layer onto a substrate. We put a mask layer on top of that. So traditionally or historically, we used to do this to coat metallic objects with a layer of protective, or let's say for making it look shiny and nice and cool. But what we used to do is that, let's say you take an armor and you basically put a layer of zinc on that entire armor, right? So that was for chemical protection, and there was no masking. So the entire structure was covered with your new material. In micro electromechanical systems processing, well, that's not good enough. We want to have control over where the material goes and what the shape of it is. So what we do is that we deposit the seed material on our wafer. We put a mask on top of it, right? So we put, let's say, a polymer structure that is used as a mold, and we cover most of that wafer with that polymer and just create openings where we want to have our structures to show up. And then once we do that, we put this in a proper salt solution, apply an electric current, and what you do is that you dissolve your source and transfer the ions, or usually these are metal ions, from the solution onto your substrate. And you keep doing this until you have the desired thickness of the material onto your substrate. Once you're done here, you go and remove the mold. And what you're left with is a metal that grew on top of your silicon through the openings of your mold. And if you don't need, you can remove the seed layer after that step as well. So electroplating, one advantage of it for MEMS is that it lets you grow very thick layers of material. So in CVD or PVD, your thicknesses are typically limited to a few microns, maybe 1 or 2 microns in most situations, in many cases less than a micron. With electroplating, you can go many hundreds of microns in thickness. You can have, as long as your mold is okay and as long as you manage the stress in your deposited film, you can have structures or films that are hundreds of microns in thickness. There are 2 flavors, DC plating and AC plating. So DC plating is where you apply a DC field and you just keep removing the material from the source into the solution and eventually onto your substrate. In AC plating, you still have a DC field that is in that same direction. So you're removing material from the source and eventually onto your substrate. But you do it in pulses. So you remove a little bit of material from, let's say, let's look at the substrate side. You deposit a little bit of material here, then you reverse the current and you remove some of it. And then you deposit more and then you remove some of it. And on the source side, it's the opposite thing. You remove some and then you put some of it back. You remove some and you put some of it back. The substrate side is where we are interested in. By doing this, you actually pack the film more closely, more tightly. And you remove whatever that is loosely attached to the substrate, to the surface. So AC plating usually gives you a better quality film. And actually, it can be even faster than DC plating, because what you do is that you can break through the boundary layers that you have at both the source and substrate by doing an AC plating. But the main advantage is getting a better quality film. And here is an example of a gyroscope that was made using an electroplated film of nickel. The typical materials that we electroplate are nickel, copper, and gold, with nickel being the most common one. And the reason for that is that we can actually have nickel layers that are fairly low stress. With most other metals, we have some stress in the film after the electroplating. The next topic is wafer bonding, and this is a necessary step, as we mentioned before, in your microfabrication process flow, where you need to protect your MEMS device. These are fragile micromechanical systems. I need to protect them from the environment. I need to make sure that they are not damaged. That's at the very minimum the purpose of bonding. There are other reasons that you may want to do wire bonding. There are different ways of doing that. So taking one wafer and bonding it to another wafer. You can have anodic bonding that we will talk about quickly. Fusion bonding is for silicon or oxidized silicon only. You can have low temperature glass bonding, thermocompression bonding, eutectic bonding, all sorts of different ways of bonding two wafers to each other. And as mentioned, these are the typical applications. You can have packaging, right, is one major application for bonding. You can have multi-layered structures. You can have a piece of silicon on top of a piece of, I don't know, silicon dioxide and then something else on top of that. You can create cavities this way. So if you have a wafer, you pattern it, you create openings here, you remove some of the material here and bond it to another wafer. You have a sealed cavity in that region, which you can use to, for example, make a pressure sensor. You can create gaps between capacitive electrodes and so on and so forth. So, fluidic devices, you want to have channels and you don't want to have open channels. So this way you can pattern your channels through your etching techniques or whatever pattern transfer technique that you have, and then close the channels from the top so that the fluid can flow through the channel. Anodic bonding is an interesting bonding technique, so I just quickly mention how it is done. It is a bonding between glass and silicon. Your normal glass, well, it has to be Pyrex. What we do is that we apply a large negative voltage to the glass side, a large positive voltage to the silicon side. Large in this case means a few hundred volts, 300, 400 volts. And by applying that voltage to the glass side, you have sodium in your glass, right? So what you do is that you move the sodium is a positive ion, towards your negative electrodes. You also have a bunch of oxygen ions at the surface that are going to be attracted towards the positive voltage you're applying to the silicon side. So the negative ions of oxygen move towards silicon, the positive sodium ions will move up. At the interface between glass and silicon, you will have a very strong electric field. You have a positive voltage applied to the silicon, and you have all those oxygen atoms lining up at the surface. If you raise the temperature, you let those oxygen ions to penetrate into the silicon, you form a permanent bond between glass and silicon. And then you can lower the temperature after that. So it's an amazing scene when you see it in practice, that you touch the location, and as soon as you apply the voltage, usually the temperature is already high. You see the bond forming and then spreading across the wafer. So here is an example that you started the bonding in the middle of the wafer, and then very soon, because of the electrode arrangement, it looks like this. And in 8 minutes, basically the two wafers are bonded to each other. Now the only issue here is that you need to make sure that your silicon and glass heat up and cool down at about the same rate. Basically the thermal expansion coefficients are about the same, and therefore you cannot use any glass. So there are special types of glass. Pyrex is one of them, boilerplate glass is another one, that have the same thermal expansion coefficient as silicon, so that when you cool down this combo from 400 degrees to room temperature, glass will survive it. Usually if it is regular glass, it just shatters. Or silicon may shatter as well, but silicon is usually much harder than your glass. Silicon fusion bonding is basically bonding two silicon layers at very high, silicon wafers at very high temperatures, silicon to silicon. You may have a layer of oxide in between them. Eutectic bonding is between metal and metal. So some metals like gold and tin, they have an alloy whose melting temperature is below the melting temperature of both gold and tin. And what you do is that you put gold on one wafer, tin on the other wafer, put these two on top of each other, press them to each other a little bit, raise the temperature. If you hit the eutectic temperature where you form the alloy, at the interface between the two metals, you will form the alloy, it melts, and you actually form a really good seal or bond between the two layers. Thermocompression bonding is the same process, but instead of relying on the eutectic process, you basically apply pressure so that the two metal layers basically are forced to diffuse into each other, and by raising the temperature and then keeping the pressure on, you form a permanent bond. A special case for bonded wafers that has a lot of applications in MEMS is for making silicon-on-insulator wafers. We will see later on when we discuss the process flow development that in a lot of cases it makes the life of a process engineer much easier if you have access to a silicon layer that is sitting on top of a dielectric layer. Very simple reason for that is that electrical isolation between different parts is now easy. If I etch a piece of silicon and isolate it, let's say material-wise, from the rest of the structure, it is also electrically isolated from the rest of the structure. But there's other advantages to it as well. So what we do first, the bonding of two oxidized wafers through fusion bonding is the, let's say, first method that comes to mind. So you take two wafers that are oxidized, you press them to each other and raise the temperature, and if you do it right, you can actually end up with a silicon on the top, oxide in the middle, and silicon at the bottom. If you want, you can thin down one of the wafers to the desired thickness. So let's say if you want only 50 micrometers of oxide, silicon on top and 1 micron of oxide underneath. So you can start with two wafers that have half a micron oxide on each other, on both of them, bond them to each other, and then thin down the top wafer through a CMP process to about 50 microns. So this is the obvious solution. Good thing here is that you can have any thickness of silicon that you want for the top layer, and almost any thickness of the oxide that you want for the middle oxide region between the two wafers. It's called buried oxide. So the top layer is usually called the device layer because I make my MEMS device out of it. The oxide that is between the two wafers is called buried oxide because it is buried underneath the device layer. And the bottom wafer is used for mechanical handling, and it is called the handle wafer. An alternative technique is to implant oxygen into your regular silicon wafer. So similar to what we did for doping, if you go and implant oxygen at the desired depth and then maybe raise temperatures to form the silicon dioxide layer, you can have SOI wafers that way as well. It's a bit trickier. You cannot really have that much of a depth here. You're limited to maybe a couple of tens of nanometers. But in case that your device layer has to be very thin, that's an alternative technique that can be used. So liftoff is a technique to deposit a metal layer, a patterned metal layer onto your substrate without using any etchant. So in this case, somewhat similar to electroplating, you first create a mold, the pattern that basically the reverse image of the pattern that you want to have onto the wafer using usually photoresist. This mold, once it is created, you cover it with metal, and in this case we use evaporation, not sputtering, so that everything is coming down vertically. You only cover the flat surfaces, and the sidewalls are not covered with any metal layers. And because the sidewalls are exposed, if I dissolve the polymer in a solution, I get rid of the metal layer that is sitting on that polymer as well. So this way I get a patterned layer of metal onto my substrate. If I do it right, it can be very clean. And the good thing here is that I don't really need to use any chemicals that remove the metal layer. The etching part is not necessary here. I get a pattern automatically onto my film. Other technique that I wanted to talk about, we mentioned this earlier when we talked about production of silicon wafers, is chemical mechanical polishing. This is a process that I use to smoothen up the surface of my wafer. That can be rough because I just use the saw to cut it off an ingot, or it could be rough because I have deposited a lot of films and etched them, and deposited and etched them, and now it is becoming rough. The process is about basically slowly polishing the surface. I use a slurry with some particles in it and start rubbing the particles against the surface of the wafer, and depending on how rough I want or how smooth the final surface to be, I can use different levels of, let's say, pressure, different types of let's say slurry, and all those things. And at the end of the story, I can actually have smoothnesses on the order of atomic levels if I do it right. So here's a picture of where we can start from and where we can end, right? So you can go from surface roughnesses on the order of microns or maybe larger than microns to something that is nanometer level, that is smooth on the order of nanometers. And those are the film deposition and processing techniques that we wanted to talk about in this course. This is enough for what we need, and then of course there's a ton of additional information that you can find in other advanced courses or in more dedicated let's say, textbooks. A lot of the material that I mentioned here, each one is a separate graduate course in a lot of departments, like vacuum systems or such and such. But this is enough for our course here. The next topic is going to be photolithography. It's about how I transfer the pattern from the layout that my MEMS engineer draw onto a wafer for processing. So photolithography is the next topic, followed by etching, and that will be the processing step of our course, and then we get into the mechanical aspects after that.